Is it a non-negative function? Can we check if it is non-negative? That means under what condition will it be non-negative? What is f of 1? We have f of x equal to c over 3x. X belongs to n. We know what natural numbers are, capital N. So what is f of 1? Anthony? Pardon? C over 3. What is f of 2? So now you are seeing a little bit of what it is. Can it be negative? Under what condition will it be negative? If C is negative, so we will have the condition that C is positive. Actually, let's say that C is positive. The second, we want to do sum of C, 1 over 3x, is equal to 1. We want to solve this equation for C, x from 1 to infinity. So this is equivalent to C, sum of 1 over 3x, x from 1 to infinity, is equal to 1. So now let's compute this one. To compute this one as we did last time, let Sn be equals to sum from x equals to 1 to n (1 over 3x). And you know what this should be at this point? You remember what this is? We can start either from 0 or from 1, but we are starting now from 1. This will be 1 over 3 plus 1 over 3 squared plus 1 over 3n. We did this last time in general. We did it last time for 5 over 6, I think. We can do it for any number r. I think we did it for x, actually. We did it for x in general. And we say that it is 1 over 3 minus 1 over 3 n plus 1 over 2 over 3 here is 1 minus 1 over 3. Can you do this computation on your own by now? Remember, I will not do it on board here. If I want to do the sum of Rn, if I want to do the sum to infinity of Rn, let's say from 1. I first do Sn from 1, right? Of Rn. And I say this is R plus R squared plus Rn plus Rn. Then I will do Rsn is infinity. R squared plus R cubed plus Rn plus 1. Then I will do Sn minus R Sn will be Sn 1 minus R. This R will remain, and all of this will go, and I will have if R, I am choosing different letters so that you get used to understanding what it is. Last time I did it with X, then I did it with 5/6. Now I'm doing it with R, and I want you to see that we can apply it also for R equals to 1/3. So now, the sum from 1 to infinity of R, I'm sorry, not R, of 1/3x will be the limit of Sn. I meant here Sn. Taking the limit of Sn as n tend to infinity. And we say that this limit will be 0. The limit of 1/3 n plus 1 will be 0. So we will have 1/3 divided by 2/3. Which is equal to what? Which is equal to 1/2. So this quantity is 1/2. So C/2, I'm sorry. Yeah, C/2 is equal to 1. So C equals to what? C equals to 2. So now as homework, you want to show that please practice this as homework, exercise. Show that if x is equal to the set of natural number, x is equal to the set of natural number. This n is 1, 2, 3, 4, 5 to infinity. Then P of x equals to the sum of 2/3x is a probability distribution function. On x. Let's do this before Friday so that I see what you can do. X is from 1 to infinity because x is n. When I write like this, x is from 1 to infinity. I'm sorry. Not this. I'm sorry for this. Look, this one is not there. It is exactly this function I'm trying to write. It's 2/3x. 2/3x. You put the sum when you want to do to show that the sum equals to 1. Last time we were doing finding the variance, and I left with the feeling like something was not correct with what we were writing. Unfortunately, I don't know. Can you see the last thing we did last time? Last thing we did. That's what we can focus on. No problem. So we define the variance. I just put another example here. It's a little bit different. Is it the same as what you have? Because I wrote this letter to complete my PowerPoint because it wasn't on the PowerPoint. Is this the same distribution that we had in class? So did we complete this actually? Is that correct? Okay. So when I was doing it at home, it was like I forgot to square the two. I was feeling a little guilty about that. So you have to square this one. Sometimes because one was square and it was 1, minus 1 was square and it was 1. And then I felt like, did I really have 4 here in class? So if sometimes when I'm doing something, you know it already. If you see me doing what I'm not supposed to do, just remind me. So now we want to do the linear transformation for a random variable. We want to find the variance of a linear transformation. A linear transformation is ax plus b. You know that as a linear function. So the variance of ax plus b is a squared variance of x. So the proof for this, I don't know whether we need to do that. Anyway. If L is equal to ax plus b, show that variance of L is a squared variance of x. And we will see that the variance of L will be E of ax plus b square minus E of ax plus b by definition of a variance is E of x squared minus E of x squared, if you can understand the difference. The first one is E of x, the square is in the bracket. The second one, the square is out of the bracket. If we have that, then this will be equal to E of a square x squared plus 2abx plus b squared. This, I think we can all do this. That is the square of the sum of two things. It's essentially the same thing we are going to do here because we know that from the property of the mean, E of ax plus b is a, E of x plus b, which we will square. So this is going to be equal to E a square x square
plus E 2abx plus B squared. By the property of the mean of its constants is that constant. B squared is alone without x. Now minus, I'm going to do this one directly. It's essentially what we have done. It's essentially what we have done here. So it's going to be with the minus a squared e of x squared minus 2ab e of x minus b squared. I know I did it. I saved time to do that. I just put the minus, but just square a e of x plus b. A e of x stand like one term, b is the second term. I square it and using this property of squaring. So having that, this is a square e of x squared. The first term here is a square e of x squared. The second term is plus 2ab c of x plus b squared minus a square e of x squared minus 2ab e of x minus b squared. You can see that this and this will go, this and this will go, and we will be left with a square e of x squared minus b squared. I'm sorry. Minus a square e of x squared, which is a square times e of x squared minus e of x, which we know is a squared times variance of x. So this is the proof of that result. We see that b is gone. It makes sense because if a distribution varies in a certain way and you add the same constant to all values, the variation is not going to change, but it will remain the same variation. So as you can see here, the standard deviation as we can see here, the standard deviation is, I can say here that the standard deviation sigma L is equal to absolute value of A times sigma X. That is the square root. If you take the square root of A square, the square root of A square is absolute value of A. For example, if A equals to -2, the square root of -2 square is the square root of 4, which is 2. It's no more -2, it is 2. So the absolute value, so the square root of A square is absolute value of A. Unless A is positive, then it will be A. If A is negative, it will be absolute value of A. So there is an example here. I'm going to skip that. Like L equals to 5 minus 2x. So essentially, I want you to see how it will behave. So mu equals to 20, sigma equals to 3, L equals to 5 minus 2x. The variance of L will be minus 2, that was A squared, times 3, 3 was sigma squared times 3 squared. So 4 times 9, 36. So sigma equal to square root of 36 equals to 6 for the linear transformation of x. Now, very important to distributions is the standard distribution. The standard distribution Z is defined as x minus mu over sigma for any random variable x. So the particularity of this standard score, or called the Z-score, is that it has a mean of 0 and a standard deviation of 1. So let me explain that here. X is a random variable with mean mu and standard deviation sigma. Z equal to x minus mu over sigma. Then Z is a random variable called the standard score. That's on the PowerPoint, called the standard score. So whenever you are given the standard score, you know it has mean 0 and standard deviation 1. The mean of Z will be P of, we can write it as x minus over sigma minus mu over sigma. We can write again Z this way by separating the fraction, which is 1 over sigma P of x minus mu over sigma, because mu and sigma are constant. They are constant. They are fixed number. And this is equal to mu over sigma minus mu over sigma equals to 0. So the mean of the standard score is equal to 0. And the variance of the standard score, using the formula we just established, that is thinking about this as 1 over sigma x minus mu over sigma. Mu over sigma minus mu over sigma here stands for B in a linear transformation. It's like the B minus mu over sigma is like our B, and 1 over sigma is like our A. So the variance of Z will be 1 over sigma square variance of x, which is 1 over sigma square times sigma square, which is equal to 1. All what you want to do is to make sure that each of these steps I am taking, you understand why I am moving into it. That is your own gain in the proof that we do. You might not be able to just prove everything I do. You can be able to prove some. You can practice doing it. It is good for yourself, for your knowledge and your training in mathematics. But at least be able to agree that I understand why he's moving from this step to the next step. So that is the standard score. So the standard score is a random variable with mean 0 and standard deviation 1. It is very useful in normal distribution, especially when you don't have a calculator, which most of you have, but the standard score is useful. In some proof also, we simplify things using the standard score. We are going to see some of it as we move on. So we are going to do 2 theorems. I hope we have about 15 minutes. But if we do the first one, the second one, the measures of variation, the Markov inequality. The first theorem we want to prove is the Markov inequality. The Markov inequality states that if a random variable is not negative, and you are giving any positive numbers, the probability that a random value will be bigger than your positive number is less than the mean divided by your number. So this is an estimation of the probability. If you have the mean of a random variable given any positive number, the proportion of values that are bigger than that positive number is less than, or is at most mean divided by the positive number. I have the proof written here, but it's easier. I think, do you prefer when I do it, if I am to do this proof? Okay, you are still there? If you are looking at what I'm writing Yeah, sometimes it's more difficult for me to explain what I have written than to write my own. Okay, so I want to write my own or explain it on the board. You sometimes check this thing when I put it on record on canvas. That's why I'm writing, so that it should remain there. When I write on the board, we will forget. Let me do it on the board because I have done it already on the PowerPoint. I want to explain this. Y is positive, not negative. A is positive. The probability that Y is greater than A is less than or equal to the mean of Y divided by A. This is the same as E of Y divided by A. So the probability that Y is greater than A is what? Is the sum of all the value of Y that are bigger than A. For example, in the distribution we just had here, C over 3x or 2 over 3x, in that distribution, you might want to say what is the probability that x is less than maybe pi, a number pi. We are saying that this probability is less than or equal to the mean of x divided by pi. So if you know the mean of x, you can estimate the probability. You don't need to write this. I'm just trying to explain. So when we say that probability that x is greater than pi, let's say x is greater than pi, x is greater than pi is probability of 4 plus probability of 5 and so on. Because pi is 3.12. If I say x is greater than pi, it's the sum of the probability of the terms for the values of x that are bigger than pi. So having that, I can write this. So now, I will say this is less than or equal to the sum of yi over a. Because yi over a is greater than 1. These are the values we have. Each of these terms is yi over a will be greater than 1 by this. So this one that is multiplying p of yi, I will replace it with yi over a, and write here p of yi. So now, I'm going to say that this is true when yi is bigger than a. This is less than that here. Now, that means if you think about what I say here for pi, if a equals to pi, I'm starting for p of 4, p of 5, p of 6, and adding them up. So I can as well say that if I add the terms that we're missing here, I will increase that expression because they are all positive. So this is again less than or equal to for all yi over a, p of yi. This is now for all y, not just those that are bigger than a. And this is equal to 1 over a, sum of yi and p of yi. And this is equal to 1 over a times e of y. E of y is sum of y times p of y. That's what you have on this that I'm trying to type. Typing is a little bit difficult. So now the next theorem, which is the Chebyshev theorem. For those who are doing statistics, you would have come across the Chebyshev theorem. The statistics, I just tell them that the Chebyshev theorem is the proportion of values that are within k standard deviation from the mean is at least 1 minus 1 over k squared. Let me write it that way. I'm rewriting in another way. just here. That x be a random variable. With mean mu and standard deviation. Each time we have a random variable is to put mention the mean. And Dasha, are you okay? So now let me explain the meaning of each of these expressions. Look at these two. I will write first that the proportion of values that are within a standard deviation, a greater than 1. Standard deviation from the mean is at least 1 minus 1 over k squared. So within k standard deviation from the mean of each distribution, you have at least 1 minus 1 over k squared values. So think about it. What is the meaning of within k standard deviation? This is the mean. So within one standard deviation, we will be here mu minus sigma, mu plus sigma. At this level, I can say the distance of the point to the mean is less than 1 standard deviation. So we will express this, that a value is within this range if x minus mu is less than x is in this range, and this range is mu minus sigma less than x less than mu plus sigma. So if you subtract mu from each of this term, you have minus sigma is less than x minus mu less than sigma. As some of you who have done some Jacob, the real analysis, we say that if that absolute value of x is less than a, if and only if minus a is less than x less than a. That is the expression we have. So this is for 1, for k equals to 1. For k equals to 2, we will move 2 standard deviation, mu minus 2 sigma, mu plus 2 sigma. So when you are here, any value x here will be saying you are within 2 standard deviation from the mean. And this will be satisfied. We put 2 here, 2 here, 2 here. So you understand the meaning of within 2 standard deviation, within 3 standard deviation. Now it could be within 1.5 standard deviation or 1.2. So observe that we are choosing k greater than 1 because 1 over k squared will be less than 1 and this number will be positive. Otherwise, there will be no meaning to say that. So that is why we will write this as probability that absolute value of x minus mu is less than k sigma is greater than or equal to 1 minus 1 over k squared. The opposite of this statement, which is this second one, this is the one I like using. The opposite of this statement, look at this, less than or equal to k sigma, greater than. So the opposite of it, this one is equal to 1 minus probability that x minus mu is greater than or equal to. It doesn't really matter much. So this one is equal to that. It's greater than or equal to 1 minus 1. This one will go, and this will be probability that x minus mu greater than k sigma. Then we will reverse the inequality. 1 over k squared. What I'm trying to explain first here is that these 2 statements are equivalent. So to prove this, we will use the Markov inequality. To prove this, 2 minutes. I will say you can complete the proof. I will use 1 minute and then we go. Look at what I will do here quickly. So z is equal to x minus mu over sigma. That's the z I put there. What will be z squared? Let me put sigma square z will be x squared minus 2 mu x plus mu square. So e of sigma square z will be e of x squared minus 2 mu e of x squared, e of x plus mu square. So this is equal to e of x squared. Mu and e of x is the same thing. This is 2. Observe here that this is e of x squared minus 2 mu times mu minus 2 mu square, because e of x is mu plus mu square, which is e of x squared minus mu square, which is sigma square. Do you see that? It is sigma square. So sigma square e of z equals to sigma square. So e of z equals to 1. So you will complete this proof by just exactly applying the Markov inequality, taking z square as a negative variable with mean 1. And that takes care of this big theorem.